Full screw. Glasses on, or I'll be right on the back of my hand for days over. We have talked about equilibrium in three primary contexts since we started. Gas phase reactions in equilibrium, gas, solid, liquid, that's called a heterogeneous equilibrium, those all go together. And we looked at Kc expressions from those, products over reactants. In the acid-base equilibrium, we've looked at a liquid phase ionic reactions and ionic ionizations and composed equilibrium expressions from those. Now we come to the third idea in equilibrium, and that's precipitation. Precipitation indicates that a salt, whatever it is, has a very, very low solubility, or some bases and acids that show very limited solubility in water. And that's what this chapter is all about, determining solubilities and how much ion is in solution and so forth in terms of molar concentrations and so forth. So when we look at this, we're going to be looking at, well, first, solubility of salt ions in aqueous media. And from there, we'll build into some more. We'll see common ions here, and you will see complex ions, which you have not been exposed to. The solubility that I'm starting with is what we call the normal. What is the solubility of lead iodide in pure water? Okay, then we throw in a common ion, say lead nitrate, and what's the solubility now? It's the same idea as common ions that you are playing with in the acid-base issue. And then we'll have a complex agent that we'll put in, and it will act like, say, a strong base. You add it to a buffer, and it'll take out the hydrogen to remove it, and it'll shift the equilibrium to the right. And that will increase solubility of the salts. So you'll have a normal solubility, a decreasing solubility type calculation, and an increasing solubility type calculation called complex agents. Anyway, so we want to start with the solubility of salt ions and how the solubility product expressions are developed. Salts ionize 100%. But not all salts have the same solubility. We've mentioned that several times before. Salts are the same thing as saying an ionic compound. And except for ammonia derivatives, everything we will use will be metal plus nonmetal. So if we look at sodium chloride, aqueous medium, you can expect it to ionize at the metal, and anything behind the first metal is the anion of that compound. It can be a single element or it can be a polyion. Nothing new here, I know. Then another one, lead iodide, aqueous, and that one will ionize 100%, and plus 2 aqueous, Pb, aqueous, plus 2 iodide, aqueous, like that. How about aluminum hydroxide? There is a point to my making this list. Aluminum plus 3 aqueous plus 3 hydroxides, aqueous. Okay, and one more that I want to use. Okay, that's magnesium arsenate. Back up in my batch here. Of course, this ionizes to 3 magnesiums plus 2 aqueous plus 2 arsenate, 4, and that's a 3 minus aqueous here. In the first example here, I mean, nothing here I would assume is a major visual problem for you. You know that the first metal is the cations, and then the anions or anything after the first metal. Okay? Now, what you may not be noticing here, you may be noticing, the first example is a 1-to-1 ionization ratio. When that sodium chloride and potassium chloride or any of those ionize, it's a 1-to-1. 1 mole of sodium chloride will deliver 1 mole of sodium ions and 1 mole of chloride ions, right? The second one is a 1-to-2 ionization ratio. Okay? Of course, we go on down a 1-to-3 ionization ratio and a 3-to-2 ionization ratio. Now, in a couple of cases, you can have a 2-to-1 ionization ratio or a 3-to-1 ionization, and they're pretty much the same in the place I'm going. So I'll show you why. Now, point is, our objective in working with what we call solubility product equilibrium is to determine the solubility of a salt in aqueous media. How much will go into solution? Whatever does go into solution will ionize 100%. I have to keep emphasizing that because I don't want you to cross solubility and degree of ionization. Solubilities are different. There's a long list of K values for salts. But whatever goes into solution will break up and you will have no molecular forms of salt in solution. Okay, now I'm going to change. Instead of a 1-to-1 from sodium chloride, I'm going to use silver chloride. That is very, very low solubility. So what we're going to do is we're going to take some silver, solid, powder, whatever, however you want to look at it. Let's see if I'm going to do it this way. Now let's do it from the salt because this is a little too complicated right now. Silver chloride aqueous means that you're going to put this in water like this, liquid. And what's going to happen is the silver and the chloride are going to become hydrated, and you will have a silver plus 1 aqueous and a chloride minus 1 aqueous, and these are hydrated, surrounded by water, coordinated with water. Now write the equilibrium expression for this. We go KEQ, products over reactants, as we always have. And in this case, it would be silver ions, and I'm going to leave the A, it's all in water, chloride ions divided by silver chloride, solid, and H2O as a liquid. Now that's the standard type of expression that you need for this. And have a good day. But the issue is these two down here in the denominator. These are infinitely high in terms of their concentrations. You will have, if you were looking at a precipitation of silver chloride, you would have a layer in the bottom of the container. I'm going to make some in a few minutes. And the amount of water compared to what ions go into solution is also infinitely large. So what is done when part of the expression is so out of balance, so to speak, with the other components of the expression, is these are considered to be constant, and this is rewritten in this capacity. Like that. And just shows the items that are delivered into solution. This is redefined as a KSP, which is solubility product constant for the salt. And so the solubility product constant expression for silver chloride in water is KSP equals just the ions. And I'll go ahead and put the AQs back in there. And this is the way you will write all of them. However, there is a little difference because of the degrees of ionization. This is a one-to-one ionization. So if you had a one-to-one silver bromide, it would enter into solution in this capacity, like that, and your KSP would be only in terms of the products. And since that is a one-to-one, that's the way you do this. And so your problem will involve molar concentrations of ions as well as a KSP number. You should be comfortable with the idea of equilibrium constants, acid and base equilibrium ionization constants, KW constants, and those were used in the acid-base issue. And so molar concentrations also used extensively in the acid-base equilibria issue. Okay. So we have an expression for a one-to-one ionization right here. So how can I take this and determine an equation for solubility? I want to determine solubility in terms of KSP numbers, because there are KSP numbers published in tables like this. Okay, as you see, and those are given, or all the ion concentrations are given and you calculate it, and we'll get there. Now looking at this right here, we have the ice table, and you look over here at the equilibrium expression over here. Does it contain the silver bromide as a solid? No, it doesn't have it anywhere in there. So we're not interested in this at all. Okay. If you drop silver chloride starting from solid into a container of water, it would ionize in the same capacity that we apply the reactions. They're all in the starting gate right now, and nothing has happened, and then we drop it in water and we get increases, X and X in pure water, and at equilibrium we have this. X is the concentration of ion that defines the solubility of the salt. X is the concentration of ion that defines solubility of given salt in solution. In each case, regardless of the ionization ratio, your objective is to find out what the value of X is in moles per liter and report that in context as the solubility of the salt. Even though it's an ion concentration, the ion here, silver and silver bromide, are 1 to 1. 1 to 1. See that? You will be looking in the other ionization ratios for the same thing, X. But one of them may be squared up here. And that's not the one you look for. You look for one over here that's not squared. We'll get it in here in just a second. So, this is solubility. So we were looking for X. Now, we want to apply this equilibrium row to the KSP expression, and to get the solubility. Now, we'll look up the KSP. It will be given if this was the kind of problem that you were trying to work. For silver chloride, 1.8 times 10 to the minus 10 is a given. So KSP for AgCl is 1.8 times 10 to the minus 10. No units are needed here. So that minus 10 tells you there ain't many ions floating around in solution. Very, very low concentrations, right? Okay, extent of reaction is very low. KSP is equal to the silver concentration and the bromide concentration. So we come right out here. Like that. And once you get this far, what do you substitute for the silver? Well, X. Okay, so I'm going to come over here and do X. There's for the silver. The bromide also is X. That's how much was delivered into solution from the silver chloride. I'll say that again because it's going to be very important that you learn to think in that context. X is the amount of ion delivered into solution by the salt and defines the solubility of that salt. Okay, so of course this is X squared. So now X squared is equal to 1.8 times 10 to the minus 10. Everybody still with me? So now this will give you X to equal the square root of 1.8 times 10 to the minus 10, and now you can tag this with molar concentration. And that's 1.34 times 10 to the minus 5 molar in silver and chloride ions. It's also interpreted as the solubility of silver chloride is equal to 1.34 times 10 to the minus 5 molar. So 1.3 times 10 to the minus 5 mole per liter of silver chloride will deliver 1.34 mole times 10 to the minus 5 mole of silver and 1.34 times 10 to the minus 5 mole of chloride. All right, that is a 1-to-1 reaction ratio. So what we can do is come up with a generalization here for all 1-to-1 ionizations. Solubility of any salt that ionizes 1-to-1 is the square root of the KSP. So you can go in the book, pick up 1-to-1 salts, take square root of the KSP number, and that's the solubility in moles per liter. Okay. Capital M. Okay, what if you did not have a 1-to-1 ionization? You have a 1-to-2 or 2-to-1. You can derive an expression that defines that solubility also. I want to use lead iodide. There it is right here. So using lead iodide, and it's a solid, and its KSP is given 6.5 times 10 to the minus 9. Right there. Now, in acid-base equilibrium, we were working in the 10 to the minus 3, minus 4, minus 5, on to the extreme cases, probably some minus 10 and 11s in some of the real weak bases and so forth. Here, you're going to see things go to 10 to the minus 50. So meaning that the salt that we're talking about almost has no ions in solution, but you using techniques here, you can still calculate the ionization concentrations. Okay, this is a 1-to-2 ionization, as you see. And we'll write an equilibrium. As here, there's aqueous, of course. Should put AQ in there and AQ there. In the ice table, the same issue exists. We disregard the solid because it's not going to be part of the equilibrium expression. Only the product side will be the KSP equals the product side. And so nothing over here will be in the expression, so we'll disregard it. However, you must note that when you deliver something on the product in ionization, it's going to deliver 1 part in metal, in this case lead, but 2x in the amount of iodides. That's a concentration number. And you bring it down to the equilibrium rows. Now write the equilibrium expression, KSP, for the salt, which is 1 part lead plus 2, and the iodide concentration. Now don't get confused on this. This has got a subscript of 2, so we need to put a square up there. That's what makes the difference in solubility expressions and calculations between 1-to-1, 1-to-2, 1-to-3, and so forth, is that some of them are in powers. And the second thing is, this is a concentration of iodide. What is the concentration of iodide that I would put there? It's 2x, not 2 iodides in here. It's 2x. Everybody got? Okay, so whatever you come out here with at that equilibrium point is the amount of iodide going in. And if it says 3x, you put a 3x for iodide, or 9x, or whatever is there. But the expression only shows one iodide because that's all the expression is delivering. Well, actually, there's two of them in the ionization, but in writing the equilibrium expression, it's KSP is 1 to 2, and that 2 is a coefficient and is used as a square. So we go forward to get x times 2x squared. See that? Does that make sense to you so far? It's just the equilibrium rule applied to the expression. And this, of course, I can make over here, is x times 4x squared. And then we get 4x cubed when we simplify everything. So KSP equals 4x cubed. And a moment ago I said X always defines the solubility of the salt. So solve this expression, 4x against the KSP, and X is equal to what? The cube root of KSP over 4. So this is a generalization for 1 to 2 or 2 to 1 ionizations. The solubility X put an S down there if you want to. Solubility X is the cube root of KSP over 4. So one of the things you need to do is pull out your owner's manual on your calculator and be sure you can manage cube roots, cubes, squares, and powers, and roots of powers, and so forth. So using the data that we published a moment ago, what is solubility of lead iodide in water at 25 degrees C. All of these numbers I'm giving you are standard thermodynamic numbers at 25 degrees 1 atmosphere. So solubility always is X, which in this case is the cube root of KSP over 4 as derived in this above, and that's the cube root of 6.5 times 10 to the minus 9 over 4, and that will be in moles per liter. So I have a solubility of 1.18 times 10 to the minus 3 molar. So in the conclusion idea, we could say the concentration or solubility of lead iodide is this number. But what is the concentration of lead? And what is the concentration of iodide? Lead is 1 to 1 with the salt. So that's also 1 to 1.8 times 10 to the minus 3 molar. But iodide is 2x. That's what I was telling you why this is so important that you recognize that the concentration. And so it's 2 times 1.18 times 10 to the minus 3 mole per liter. Given 2.35 times 10 to the minus 3 molar in the iodide ion. So you see the 2x in there has to be included, and depending on how the problem is delivered to you. Okay, so let's say we want a solubility expression for 1 to 3 or 3 to 1 ionizations. Aluminum hydroxide is a good example. Starting as a solid, will ionize very nicely to aluminum ions plus 3 aqueous plus 3 hydroxides minus, and that will be aqueous. I shouldn't put parentheses on that part. 3 OH minus aqueous. There we go. Like that. Its KSP number is 4.6 times 10 to the minus 33. So we need to derive a solubility expression for a 1 to 3 or 3 to 1, same thing, ionization. So using the ICE table, I have to rewrite this to aluminum hydroxide, aluminum plus 3 OH minus, like that. Don't need this. Ionization is 1 to 3, sorry. We start off with 0 and 0 and deliver X and 3X this time and have X and 3X at equilibrium. Yeah? Again, the solubility product expression is only in terms of the product side. Remember, the salt side or the reactant side is ignored. So we don't have anything here. So the KSP for this one is aluminum plus 3 times the concentration of hydroxides delivered solution cubed, because it has a coefficient of 3. And we didn't have that power to the raised to some power in acid-base equilibrium, because everything was a 1-to-1 ionization. Even with the polyprotics, it ionized in first step, second step, third, or whatever. And so the equilibrium row is now applied, and we have X times 3X cubed, which is X 27X cubed, and X, which is equal to solubility, is equal to the, that adds in to fourth root, or go ahead, 27X to the fourth, and we solve for this against the solubility, this, X is equal to the fourth root of KSP over 27. So now we have 3 equations that you have to deal with. They can either be derived, or you can memorize them. You can have questions as what's the solubility of such and such in pure water. Okay, so we want to find the solubility of aluminum hydroxide based on the KSP number given as 4.6 times 10 to the minus 33. You substitute to get X, and we have the fourth root of 4.6 times 10 minus 33 over 27. Comes out in moles per liter. Okay, so this is 3.61 times 10 to the minus 9 mole per liter of the compound delivers ions into solution, and that's the solubility. What is the solubility of aluminum? Well, it's a 1-to-1 with the compound, as you see up here. So it too is 3.61 times 10 to the minus 9 molar. What is the hydroxide concentration? It is 3 times 3.61 times 10 to the minus 9 in moles per liter. And that's 1.08 times 10 to the minus 8 molar in hydroxides. Can you calculate a pH with that? Sure you can. POH and then 14 minus POH gives you pH. So salt solutions or metallic hydroxide solutions regardless are pH sensitive, and you can calculate and generate hydronium ions and hydroxide ions and so forth like that, and those can be calculated. So the POH, just for passing here, is minus log of 1.08 times 10 to the minus 8, which y'all are all primed to do today, and so we'll take the log of that. I get 7.97. And pH, of course, be 14 minus POH. It's 14 minus 7.97. And we get a 6.03. What's interesting about that? Look at the number. What can you tell me?
It's an acid. It's acidic.
It's acidic. And we're talking about an hydroxide. So when you have some hydroxides of this context, where they are considered hydroxide salts, their KSP is so small, 10 to the minus 9, that very little goes into solution. And then whatever does go into solution doesn't go into sufficient amounts, but it still reacts with the water and leaves a higher hydronium ion concentration than the hydroxide ion concentration. So this is a kind of a twist in the details. Okay. Okay, so we want to look now at deriving an expression, solubility expression for magnesium arsenate, which represents a 3 to 2 ionization ratio for the salt. Same procedures that we've used here. So magnesium arsenate delivers 3 magnesium plus 2 ions into solution per mole, and 2 arsenate, 3 minus aqueous, like that. Set up the ice table like that. We disregard the magnesium arsenate, it's not part of the expression. And what is delivered? Well, 3x, let's do it right. 0, 0 plus 3x plus 2x, and we wound up with 3x and 2x concentrations. So we write the KSP expression in terms of the product side, raised to the powers as needed. So KSP for the magnesium arsenate is magnesium ion plus 2 aqueous, if you want to be totally correct. And then the arsenate ion squared, like that. So we substitute the equilibrium row. We have a 3x cubed for the magnesium, and we have a 2x squared for the arsenate, which 3 to 3 is 9, 3 9, 27 x cubed times 4x squared, and that's going to 108 x to the 5th. So our KSP expression now is equal to 108 x to the 5th. But the individual x is still the solubility. So you solve this for x which equals solubility of the magnesium arsenate, that's the compound. It will not be the solubility, X is not the solubility as you see for the magnesium or the arsenate this time, because more than one was delivered. But the X by itself is defined as the solubility of the salt collectively. And so that is the fifth root of KSP over 108. Like that. So 2 times 10 to the minus 20 is the KSP. So our X, which is the solubility, is the fifth root of 2 times 10 to the minus 20 over 108 molar. See what that looks like. And that's 4.503 times 10 to the minus 5 molar in that salt. So that's the solubility of the salt now. But the solubility or the concentration of magnesium is 3x. And the arsenate concentration is 2x. So you want to be aware of the equilibrium row multiples here, 2 and 3. So it's 3 times 4.503 times 10 to the minus 5 molar. And this is 2 times 4.503 times 10 to the minus 5 molar. And we got, there we go, guys. Okay, so we have 4.503 times 10 to the minus 5 times 3 equals 1.35 times 10 to the minus 4 molar in the magnesium. .006 or 9.01, I guess. 9.01 times 10 to the minus 5 molar for the arsenate. So you want to check mark and be careful. I think you see what I'm talking about. In the ionization, you'll have a solubility expression, but since the ions come in multiples, you want to be sure that you multiply whatever that solubility is by whatever given multiple you have. So if it is a 1-to-1 ionization ratio, then the solubility, we'll call it S for this one, S is equal to the square root of KSP. If it's a 1-to-2 or 2-to-1, solubility is equal to the cube root of KSP over 4. And if it's a 1-to-3 or 3-to-1 solubility, see, it's 1. There's actually, that's, you don't put a 2 in there, but it's 2, 3, 4, right here, KSP over 27. And if you have a 2-to-3 or 3-to-2, solubility is fifth root of KSP over 108. So it's just really a matter of memorizing those the denominators in each of those expressions below the KSP number. You certainly will be given the KSP. Now, on the other side, you can ask questions in different capacities, like what's the KSP given solubility? How much ion concentration given solubility? Well, it may not be the ion concentration. You may have to use a coefficient number. And so all of these are pretty straightforward if you learn those. So yes, that says minus 50. What's the solubility and what are the ion concentrations in solution? Okay. Now you first notice this is a what? 2 to 1. Same thing as a 1 to 2. So we have silver sulfide delivering 2 moles of silver plus 1 mole of sulfur. This is a 1 to 2. Solubility S is the cube root of KSP over 4. And so that's the cube root of 6 times 10 to the minus 50 divided by 4 in moles per liter. That's 2.47 times 10 to the minus 17 molar. So that is the solubility of the salt itself, the compound. That's how much of the compound breaks down. The concentration of silver ions is 2 moles delivered. So if X is 1 mole, we'll have 2X. We'll have to double it, this solubility. So that's 2 times 2.47 times 10 to the minus 7 molar.
Minus 17.
4.3,
It's minus 17.
hang on, times 10 to the minus 17. All better. So it's just a matter of learning the formulas and applying the data given to the various formulas. Do another one. Let's see if I can. There's another one in here. There we go. Four times 10 to the minus 36. Just leave it open. Okay. 4 times 10 to the minus 36, and you see you have a 3 to 2 ionization here. So lead arsenate goes to 3 lead ions plus 2 arsenate ions, 3 minus, like that. So that's a 3x and 2x at equilibrium. And so your solubility expression is the 5th root of KSP over 108. And so that is the 5th root, this side, 5th root of 4 times 10 to the minus 36 divided by 108. It comes out in moles per liter. To the minus 8 molars, what I show here. So getting the ion concentrations, the lead plus 2 from the equilibrium row is 3x. This is X solubility, and the arsenate is a 2x. Okay. Any questions about these? Okay. Show you some. Here's one. Will make an impression, I hope. Ouch! Okay. I'm going to ask the following question. What's the solubility? Which is the most soluble is what we want to do here. Let me bring this up, because this is really important in your education on this. Of each one. So the solubility of silver bromide is equal to simply the square root of the KSP number, which is the square root of 5 times 10 to the minus 13 in moles per liter. That is 7.1 times 10 to the minus 7 mole per liter. And so the solubility to compare for iron hydroxide equals the fourth root of KSP over 27 in this case. 8 times 10 to the minus 16 over See how that worked out? We got a bigger number now for something that had a smaller KSP. You got a 7.3 solubility times 10 to the minus 5, but here's 10 to the minus 16. So you can't use the solubility, KSP for solubility, unless everything has the same ionization ratio. If the question that's given, say you have silver bromide, silver chloride, silver iodide, Well, all of them have the same ionization ratios. So that means the bigger number is the more soluble. But if they have different ionization ratios, you have to use the square root formulas or whatever, the solubility formulas, and calculate each one. Everybody good on that? All right. With predicting precipitation. This topic is more in tune with which way will the reaction shift, to the solid side or to the ion side. Given an expression AgCl solid, you have very limited solubility, and it delivers ions of silver and chloride. And the KSP expression is silver and chloride, as you know now. The concentrations of silver and chloride, say, hypothetically, are such that when you multiply them together, you get a KSP number. 1.8 times 10 to the minus 10th. That's KSP. This is a condition called saturation. If silver times chloride ion concentrations equals KSP, which gives KSP equal, this is called saturation. It's a clear solution, and it's not showing a precipitant, but one more grain of silver chloride, one more molecule of silver chloride, and everything falls out of solution. Starts falling out of solution. So we're in an equilibrium issue between the solid and this. But what happens if the multiple here, the KSP, is less than the number we have here? This is where we go into Q values again. And we'll tell you that the reaction will shift toward the solid side. And if you'll do this, KSP, KSP like this, and then QSP, and QSP, we'll do the same thing we did before. But be careful here. Now, you could just put in inequalities anywhere, and the gas phase thing, because it didn't matter. It would either shift right or shift left. But you've got to be real careful. Like if you set this one up, and this is equal, if the QSP is larger than KSP, you want to be sure that your inequality points to the solid side. So you want a left shift, meaning that the ions are coming together and precipitating out of solution. That's the condition. This we just indicated is saturation. There's a thing called supersaturation that provides for higher concentrations of ions without precipitating, but we're not going to get into that. We're just going to say that everything that exceeds these Q values, the Q value exceeds the KSP number, it's always going to precipitate. So, pointing the arrow to the right means that you're going back to the ions, and that's favoring the reaction shifting more ions in solution, so no precipitation occurs at the silver and chloride ion concentrations specified. Sometimes examples go off the wall here. Okay. Okay, so barium fluoride is a 1 to 2 issue, like that, and goes to barium plus 2 fluorides. So its QSP expression being the same as the same as the KSP expression is barium times fluoride concentration squared. And they give you the concentrations because what you're doing is mixing a couple of things together. If the Q value is larger than the KSP value, we're going to get a precipitate. If not, it means it's not saturated yet. So our barium now is 0.020 molar and 0.015 squared, and see how we go out. So I see a 4.5 times 10 to the minus 6 for the QSP, and then the KSP is equal to 1 times 10 to the minus 6. So the QSP is greater than the QSP. Now when it'll precipitate, okay? But remember how I told you to set up your little memory table. KSP, 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 and then QSP, QSP, and QSP. Now, for precipitation, yes, you want to shift to the solid side. So if the equation, you set it up so that the solid side over here, or compound side, is the precipitant. So if you have that combination where the QSP is greater than the KSP, the arrow will point back to this side of the equation. And this is saturation, and that's no precipitant forms. It's a pretty easy concept, but there's a couple of cautions. One, use the right QSP to compare. It's just like the KSP, but you're trying to find it as larger or smaller or equal to. And set it up, K comes before Q in the alphabet. But when you write this equation, you must remember if you have a larger Q value in your calculation than KSP, a precipitant will form. And you want the setup to indicate that you have a left shift toward that side of the equation, solid side of the equation. Everybody kind of see the... This, in effect, is the addition of an acid to a salt solution, or a salt, to effectively increase solubility. Here are two salts, calcium carbonate and barium chloride. And both of them form chalky white powders. Okay? The calcium carbonate you will recognize in magnesium sulfates and sulfites as those salts called, precipitants that mess up your Mr. Coffee and ruin your heating elements. And you have to, what do y'all do when you have to clean out your Mr. Coffee? Anybody ever done that? Pour vinegar through it? Y'all never done that before? Okay, I'll show you why it works. One way to clean up your Mr. Coffee, so to speak, and get a little more life out of it is percolate some common household vinegar through it, because it's acetic acid. And acetic acid will function to dissolve with the magnesium sulfates and sulfites and carbonates and all the other stuff. And then this is why. Okay, take the calcium carbonate. When it goes into solution, is calcium plus 2 plus CO3 2 minus. It has a very low solubility. As the temperature goes up, salt solubilities on some salts, I didn't say most of them, but a lot of salts will go down. And this is one of them. So as you use calcium carbonate containing water, over time, if it's been heated, then it will start forming scale, some people call it, on your heating elements. Now, one way to get rid of it is to run an acid through it. It's because if you add an acid to it, you're adding H plus to that. And H plus will connect to the HCO3 and become a bicarbonate, which is soluble, which is a soluble weak acid. Let me move that out a little bit. Now, the formation of this bicarbonate removes the CO3. And leaves a void right here. So our equilibrium in here, somebody got off the seesaw right here. So which way will the reaction shift to replace that? Obviously from the carbonate to the right. Everybody? Okay? So if we're shifting to the right as the acid takes out the CO3, then, and that's soluble, then we're increasing the solubility over here. So more is going into solution. So this soluble weak acid removes the CO3 as HCO3 minus, and this increases or shifts reaction right, which is increased solubility of calcium carbonate. Okay, but if we do barium chloride, if it's precipitating out for some reason, we have barium plus 2 plus 2 chlorides. Now, if you put an acid in with this, it's going to go to HCl. Is that a weak acid? No, that's correct. No. So if it's going to form a strong electrolyte, then in changing the pH will not affect the solubility of whatever compound you want. So the rule is salt ions plus acid must react to yield a soluble weak electrolyte. And this increases solubility of the salt. So that's an induced change in the pH of a system in order to increase the solubility of it. That's one topic. used. So I got an iron hydroxide. This will be the last topic, so hang on. Iron hydroxide, iron 2 hydroxide, we'll do that one. As a solid, goes into iron plus 2 aqueous plus 2 OH minus, and it's, let me move it down here, KSP for this animal is 8 times 10 to the minus 16. These are, you will appear relatively simple to you. Well, at equilibrium, of course, we have an X and a 2X in here. And so what is the amount of hydroxide? Remember, when you apply the solubility expression in this case, it only defines X. That strike a nerve? So you got to double it. Okay, good. Yeah, everybody hear that? Understand? See, we're limited. So if we got the solubility here is equal to X, which is in this case a cube root of KSP over 4, which is easily computed, 8 times 10 to the minus 16 over 4 molar. And we'll run that out real quick, if I can find my calculator. Get 5.84 times 10 to the minus 6 molar. Y'all double check me on that one. Okay, if this is the solubility, that is simply meaning that the FeOH2 molecule will only 5.84 times 10 to the minus 6 molar will dissolve. That's what the X means. However, since iron is a 1-to-1 ionization with the iron hydroxide, it too is defined as X. So you can say the times 10 to the minus 6 molar is for iron. But hydroxides, as you see in the equilibrium row, here is a 2X. So your hydroxide ion concentration is 2X, which is 2 times 5.84 times 10 to the minus 6 molar. .17 times 10 to the minus 5 molar in OH ions. We calculate POH and pH so that's pretty straightforward, but the only complication is you must be careful with the degree of ionization. Okay, what if I give you an AlOH3? Okay, you got to use a different ionization expression. You have to use KSP over 27 to the 4th root, and then when you get that, you have to multiply by 3 this time. So, and then do your pH and POH. And so it's not a difficult issue. I just want to be sure that you hear, okay, there are different ratios going out there into the solution, and when you make your calculation, be careful you don't use X. Now, if I use something that's a 1-to-1, square root of X is OH and everything the same. Okay, so that's about it. Now, the only other topic that we've really got is common ion effect and complex ion equilibrium. And I'd like to do that next time, and y'all go home and work on your chemistry exam. And when we come in next time, I want to look at some demonstration. I'm going to save that till next time. Show you some precipitants and what they look like. Do you have any questions? Please study this stuff. I'm trying to post these online. This wasn't bad to you. What is your response to this? I mean, after being primed for the exam today, did this come across pretty easy for you? Okay, so keep it up like that makes the rest of the course going to be real easy for you if you will study on a regular basis. Got you. Hey man, how can I help you, buddy?
She's walking.
Where you going? Yeah, when did this happen? I mean, has she hit withheld?
Probably the last 5 minutes, because that's why I was about to leave.
That's fine. I'm glad you hung in, but I didn't want to go too far.
Yeah.
But the
Yeah, lots of, well, I mean, it's all...
Yeah, I remember when I had this
Baby
knee, man, I got a 12-inch scar down here, and when I got started, that first day I got out of surgery, man, that trainer came in here, you know, he's about the size of a pretty dairy boat, and he said, here, he grabbed me by the shoulders, I'm 230 pounds, he picked me up like I'm a suitcase, man. He said, all right, start walking.
I'll see you Tuesday.
Yeah, buddy. You need to get you a partner that you can deal with, and we'll schedule a time to get you and that partner that already knows how to, like that one or that one or that one, that already knows everything there is to know about the lab. And you can, yeah, this will be after the exam.
After the exam?
Yeah, you don't need to worry about lab right now. It's really easy. You know, you're going to run a time pH curve for strong titration and a strong weak titration and explain the difference between hydrolysis.
Okay.
And then we'll do a determination of Ka, which is a volume pH titration.
Okay.
And your lab partners probably know, it was really straight up. They can guide you through it. But what I try to do is, I can't do everything.
Mm-hmm.
So I'll open the lab, I will be sure to get the stuff together and you can make it up with them. Okay?
Okay. So
Sometime
anytime
after
the exam?
Yeah.
Okay,
And,
so the exam,
I don't,
this exam, we just take it home and do it and then
Yeah.
bring it back
yeah,
Tuesday?
on Tuesday.
Okay.
Go out, ready to go, and I'm going to keep doing this.
Did you pass back the quizzes Tuesday?
I haven't graded them. I've been so busy trying to.
I just didn't know if you gave them back.
No, ma'am. I've been so busy trying to build the exams.
Mm-hmm.
I had one earlier for Kim one, and then y'all's, and I'm just exhausted. And by the time I got through this thing, I said, you know, I'm gonna give it to him and go home. Yeah.
That's fine with me.
Go ahead. Now some of them are real blisters, and I'm trying to think. There are a couple. I'll send the exception stuff to you.
Mhm.
So check your email. But some of the questions, I need to make some exception notes and whatever
Okay.
for you, like I did on the last one.
All right.
And you got all your
Yeah.
adversities worked out?
Yep.
Okay.
Thank you.
Well, I was worried that
No.
he was more here, and
No, my car was like leaking.
those have a tendency to get in the way of a good education, don't they?
Yes. Yes. So.
If you run into a problem like that, you might make friends with somebody that can come by and pick you up.
Yeah.
I've had students do that before. I mean, if it broke that morning, that.
The only thing is, I live in Humble, which is
Oh,
like
that's a nice drive.
It's 40 miles away, so nobody from
Yeah, that's
here
a-
would.
Why
Yeah.
don't you go to? I'm flattered you took my course. I am, but why'd you come over here? And you take
Because
other stuff too?
I go to University of Houston, so
God, you get courage.
Yeah.
You.
so they didn't have this class available there. It was already full, and so I took one. By the time I signed up so late that
Oh, okay.
there was nothing.
That was the only bun
And
left.
I know, out of the teachers, you were the best one out of who was left.
Well, really?
Yeah.
Well, how'd you find that out?
Your ratings online.
Do I have a rating?
You have ratings, yes. Student.
Well, that's scary.
Yes.
Yes, I came out on top of 4 or 5 teachers.
Yeah, there's a few of them worse than you.
How
No,
about
but
that?
your teaching style is something that,
It fits you,
Yeah,
what you're
exactly.
doing.
'Cause
Yeah, I
people-
like to get into the explanations more than a lot of,
Yeah.
some of them
very
are more.
online stuff, doing homework online, all these
Yeah,
computer stuff that they don't teach you anything, so.
they don't do that, and I'm available 24/7 too.
Exactly. Most
And
teachers
so I
are.
try to get to everybody. Sometimes I can't. I have so many. But eventually I answer everybody's questions. Well, I appreciate you taking
Yeah.
my course then.
Yes.
I hope this is turning out to be something that will help you.
I hope so.
Yeah.
We'll
What's
see.
your major?
Biology and nutrition.
Oh,
Yeah.
you're doing the content science.
Yeah. So I'm not sure.
You're not going to be a nuclear physicist?
I don't like chemistry.
I don't think so.
No, that's too
Because
hard.
I'm glad you're back. It's,
All right.
if there was a problem beyond, I'll try to get you the help.
All right.
Okay?
Thank you. Bye.
Yes, ma'am.